Hello everybody and welcome to our first physics video of the year. This is the first unit, so we're looking at the kinematics unit. And this is lesson 1. So we're going to start with talking about scalars versus vectors. So in physics, we are dealing with different values such as velocity, acceleration, speed, distance. These are all things we are going to explore in this unit. And all of those fall within two categories. They're either a scalar or a vector. So it's important that we know what those are. So first of all, a scalar quantity. So scalars only have a magnitude or an amount or size. I'm not going to dive into that right away until we talk a little bit about vectors, scalars. Vectors have a magnitude and a direction. So the difference is that vectors have a direction. So this is why speed and velocity are actually different, because speed is a scalar. You're only traveling 100 kilometers an hour. That's it. It doesn't matter which direction you're going. That's your speed. Whereas if you wanted to know the velocity of the car or the velocity of your car that you're driving, you would have to say, I'm driving 100 kilometers an hour east or west or north or something like that, where you include the direction. So we do draw vectors as arrows. And you'll see that we actually label them a little bit differently. So I'm not going to dive too much into that because we are looking at that throughout the entire unit. So let's start with distance versus displacement. One is a scalar and one is a vector. So distance is a scalar quantity and displacement is a vector quantity. So distance we represent with small d, and displacement is also a small d, but because it's a vector, we put this little vector sign up on top of it. So it's a little arrow, it's like a little half arrow, like that. So anything that's a vector, whenever you're writing it down, needs to have that arrow symbol, and anything that's a scalar doesn't have to. So distance is the separation between 2 points. And we know that it is a scalar quantity. I already have written that down, but repetition. Displacement is the measure of the change in position. We'll explore this a little bit more. So you can say change in displacement, right? So theta here, this is theta. That's a Greek symbol theta, and theta represents change. You're going to see this a lot. So change in displacement is going to be position final minus position initial. So change always means final minus initial. And we're going to explore this a lot more. All right, so with a scalar, or with a vector, sorry, we need to have some sort of direction. So direction can be represented, I'll write this down, direction can be represented using your cardinal directions. That's your north, east, south, west, or with positive or negative values. And I'll show you what I mean by that. So let's dive into an example right here. So here we have two people. Maybe I'll move this down just a little bit. I ended up writing a lot more than I planned on. Let's move this down a little bit. So we have two people. I've set them up on a number line here. Hang on, let me move this down too. Our next example, so we're not crowded. Okay, technology. This is going to happen lots, folks. I am not good with it. So, all right, here we go. We have two people. I've set them up on a number line here. Let's name this one Susie and this one Jim, just for fun. So we have a number line here, so we know that anything in this direction will be positive and anything in this direction will be negative. If you really wanted to, you could say that this is east and this is west. So whatever direction convention you want to use, I'm okay with, but you have to be consistent. If this side is east, that way is always east, right? If that way is a positive direction, that way is always the positive direction. It doesn't matter what you're doing, that way is always positive, the other way is always negative. So let's explore this. A couple of questions. What is the distance between of Jim from Susie? So what is the distance of Jim from Susie? Well, you can see that if we counted, we can go, if these are in meters, for example, let's say that this is in meters, just for fun. We've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters. And that's in the positive. Oh, wait, it's distance is a scalar. We don't need a direction. So this is 10 meters. What is the distance of Susie from Jim? So if Jim wanted to walk to Susie now, how far would he have to go? Well, we already know he has to go 10 meters, and because distance is a scalar, we don't even need a direction. So this answer is also 10 meters. That's kind of nice. What is the position of each person? So we know that Jim is at positive 7 meters, and Susie is at negative 3 meters. So that's their position according to this number line here, this scale we have at the bottom. Let's scroll up a bit. What is the displacement of Susie measured from Jim? Maybe I'll roll this down here. Hang on. So what is the displacement of Susie from Jim? So that means Susie is the final, Jim is the initial. We know that displacement is d final minus d initial. So if we plugged those in, final is negative 3 minus, and Jim was at positive 7. So negative 3 minus 7 is negative 10 meters. And you can tell that makes sense because if we're going from Jim to Susie, and we go from Jim all the way over to Susie, that is 10 meters. And look at what direction we're going. We're going in the negative direction. So we can say that the change in displacement is negative 10 meters. We've covered the direction because we have that negative sign there, and we've established that negative is to the left and positive is to the right. We can do the opposite, right? What is the displacement of Jim measured from Susie. So the displacement of Jim measured from Susie, that means Jim is in the final position. We started at Susie, so she's in the initial position. And so we have our change in displacement is equal to position final minus position initial. We know Jim's position is at 7 meters. Subtract Susie's position is at -3. So when you subtract a negative, you can chop chop. And you've got 7 plus 3 is 10 meters, or positive 10 meters, or even 10 meters east if we are going to use east and west as our directions. So either one of those works really well. And that's kind of the difference between distance and displacement. Okay, next example. I gotta roll all this down because I ended up using a lot more space than I thought. That's okay. Okay, here we go. I'll zoom in a bit here. A polar bear walks 275 meters east and then 525 meters west. What is the distance that traveled by the bear? Well, we can draw a picture. Sometimes that's nice. So if you're not sure about your directions, north, east, south, west. So let's draw what the polar bear has done. So he started here and walked 275 meters east, and from there he then walked. I did not think this through. Man, planning today is not my thing. Let's move that right there. Then he decided that from there he's going to walk, I'll just move it down here, 525 meters that way. So what is the distance traveled by the bear? Well, the bear started moving 275 meters, then walked 525 meters, and that looks like it gives us 800 meters. So the bear traveled 800 meters total. What is the bear's displacement? So here we have to talk about, well, we know that displacement is final minus initial. So what is the bear's final position and what is its initial position? Well, we can say initially, where did it start? It started right here, right? And that'll be our 0. Perfect. Where did the bear end? The bear ended right here, right? So the displacement is going to be something like, let me get a different color here. Let's avoid red. Let's do gray. So the bear's displacement is going to be represented by the gray vector right there, because it's always measured from initial position to final position. And so we have to figure out what that value is. So we know that we can do 525 minus 275, and we will get, so hang on, 525 minus 275, 250 meters. So this gray value is 250 meters. So the bear has stopped 250 meters away from its starting point. We do have to establish the direction. So if I make right positive and left negative, that's always a nice way to do it, because when we graph and we think about it as an x-axis, to the right is always positive and to the left is always negative. In physics, you can flip those around as long as you stay consistent with it, but it is nice to have just kind of one way to do it, and then you remember. So right being positive and left being negative is always a nice way to do it. So that means the initial position was at 0, and the final position right here, that was, I accidentally hit the erase button, right here is at negative 250 meters. So our final position is negative 250 meters. Our initial position is 0 meters. So our change in, or our displacement is negative 250 meters. Hopefully that made sense. I might have over-explained it a little bit, but we'll go from there. So displacement in 2 dimensions. So in that last question, the bear walked east and then west. So we didn't really get a lot of 2-dimensional stuff. That was kind of just 1-dimensional. So here we go. We have you. You're walking 20 meters east and then 35 meters south. Oh my gosh. I just want to zoom out a little bit. I don't know why the keyboard keeps coming up. There we go. You walk, oh man. You walk 20 meters east and then 35 meters south. What is the distance that you've traveled? Well, we're going to add them all together for distance. If you've walked 20 meters, then you walked 35 meters, we know that you have walked 55 meters. Easy enough. This distance doesn't matter what direction you walk, is just the total amount that you've walked. What is your displacement? It's going to be nice to have a picture for this one. So let's start. Start here and you walk 20 meters that way, and then you walk 35 meters south. So from there, you're going to walk 35 meters south. And we know that your displacement from initial to final is going to look something like that. So this is your displacement. We need to calculate this a little bit, so we're going to have to use trig. Thankfully, we've got a right angle here. So we can do Pythagorean theorem, right? A squared plus b squared is equal to c squared. So 20 squared plus 35 squared is equal to c squared. I'm just going to punch this into my calculator here. So 1625 is equal to c squared. I will square root both sides. And I am left with c is equal to 40.3 meters. So this is 40.3 meters. So I know how far I am from my initial point, but I also need to know the direction. So in this case, what we can do is we can find this angle right here, and that will help us. So if we're using this angle, I'm going to use these 2 sides because they were given to us in our question. So that's the opposite and the adjacent. So I'm going to use my tan function if I'm looking at SOHCAHTOA. So the opposite and the adjacent is the tan function. So tan of theta is equal to 35 over 20, opposite over the adjacent. And to find that angle, we want to do the inverse tan function of our ratio. So inverse tan of 35 over 20 is 60.3 degrees. So for our answer, we can say that the displacement is 40.3 meters at 60.3 degrees. And we still need to say what direction that is. So that's 60.3 degrees. And we've come from east, and then we went in a southern direction when we measured that angle. So we would say 60.3 degrees south of east. Hopefully that makes sense, because we measured that angle from east, and we went in a southern direction 60.3 degrees. So you could say the displacement is 40.3 meters at 60.3 degrees south of east, and that would be your final answer. We will have practice problems like that, so hopefully it makes sense. I just want to talk to you, we're almost done here. I just want to talk to you a little bit about adding vectors, because we will be doing that. So when we add vectors, we want to add them tip to tail. So as you can see in our last example here, blue vector, we drew like this. And then when I added the next one, I went from the tip of the blue vector to and the tail of the purple vector. So we add them like that. It made sense for this question because we were walking, and it just makes sense when you're walking to do it step by step like that. But I will show you an example where it might not make as much sense. I'm not going to solve this. I'm just going to show you how we would add the vectors. So the example is an airplane travels north at a speed of 300 kilometers per hour. A crosswind blows east at a speed of 75 kilometers per hour. What is the airplane's resultant velocity? So if we were to draw a picture, this is our airplane. So a lot of times in physics, we just use a dot, especially because I'm not an artist, and I'm sure, well, maybe some of you are, not all of you. So the airplane is traveling north at 300 kilometers per hour, and there's a wind blowing east at 75 kilometers an hour. So from the airplane, it's blowing like that. But we can't really add them when they're like that. We don't really know what the resultant vector is, because we know that the airplane's definitely not traveling straight north because there's wind blowing it to the east. So what direction is it traveling? So when we add these, it's good to add them tip to tail. So we have this one at 300 kilometers per hour. And then we're going to add the next one tip to tail. So from the tip of the first one, we will add our second one, 75 kilometers per hour. And then you can see that the resultant vector, let's switch to green here because it just looks nicer. The resultant vector is going to be from the start point to the finish point. So that will be the actual direction of the plane. And we would have to figure out, based off of those numbers, similarly to what we did with the walking, what this velocity would actually be if we've got these two other velocities. Hopefully that made sense. We will get lots of practice with adding vectors, distance and displacement. It's all new, so ask lots of questions, help each other out, and yeah, we'll get comfortable with all of this. Thanks for watching.